All right, let's go ahead and get started. Hello, everybody. Thanks for joining us today for the third quarterly HMS webinar. My name is Matt Fleming. I'm the acting division chief for the Water Management Systems division here at HEC and a longtime HMS team member. Before we get started, I wanted to go over some resources that are available to you that show off some of the new capabilities in version 4.11. So I'll just go ahead and put it in the chat. So this is the link to the page that you should see on the webinar right now. That's going to take you to what we call the documentation page or the tech transfer page. If you click on the training link on the bottom right, you should see access to the different classes that we've given in the last year. The basic HMS class is on top. The H&H for dam safety, the hydrology portion is right there. Advanced applications of HMS, that's new material that we gave this year. And then also some other new material that was given this year was the hydrology portion of the post-wildfire debris flow modeling with HMS class. So you can click on any of those links. I'll just choose the post-wildfire option there. And you have access to the PowerPoint files that were created and also links to different workshops that highlight the new capabilities that were delivered for post-fire debris flow simulation. Okay, so that's the training. We are going to have a number of HMS training classes in FY24. There's going to be the basic class in November of 24. There's the H&H for dam safety, I believe, in March. You get advanced classes in June. And I have heard word that there's going to be a post-fire debris class as well. So training is there. We're going to talk about the user's manual and the release notes and throughout this webinar. And then I also want to highlight the tutorials and guides. If you click on that link, you should see a number of categories that we've tried to group the different tutorials and guides. And the goal for the HMS team is anytime we deliver a new capability, we're trying to give you a couple of examples so you can see how that capability is used in a real-world application. All right, so that's the resources available to you. And then I also want to touch on, there's going to be a leadership change in the HMS team. Greg Karlovitz is the current HMS team lead, and he's led the team through the 4.10 and 4.11 development cycles. He's done an amazing job. Exciting new capability has been released to the field, and the team is growing. Part of the philosophy on the HMS team is to grow and develop leaders and provide opportunities to the team. And so next up is Josh Willis. He volunteered to be the next team lead after version 4.11 is released, and he'll lead the team through the 4.12 and 4.13 development cycles. We also want to thank all of our funding partners, the Flood and Coastal R&D program, the Mississippi River Geomorphology and Potamology program, Columbia River Basin Hydrology program, Dam and Levee Safety, the SWIMS program, the Science and Engineering Technology program, FEMA, and WMIST. Those funding partners have helped the Corps add amazing new capability to the software. I also want to give a shout out to our field testers who try the new capabilities that are provide us feedback, and also those that report bugs. Your feedback really benefits the entire community. So I know it might be a pain to send us that bug report and to zip up your project and provide it to us, but those 30 minutes that you spend are going to save other modelers time and effort in the future. So thank you. HMS 4.11 is almost finished. The HMS team has been working on 4.11 since the summer of 2022, so since last year. The team has released 16 beta versions in an effort to get what I've counted 40 new features added to version 4.11. So to get those new features out to you all so that you can provide us feedback before we make that final release here pretty soon. You might ask, when is 4.11 coming out? Final date? I don't know. The best that we can give you is very, very soon. All right, the format for this webinar includes 4 speakers. Tom Brower, he serves as the HMS team lead developer and has been instrumental in most of the new features that you're going to see in version 4.11. Then we have Josh Willis. He is an HMS developer. One of his notable contributions to 4.11 is the new ensemble compute. Mike Bartles, he's also an HMS developer, and one of his notable contributions to version 4.11 are the new snowmelt methods that you have access to. And then myself too. We're going to take turns and go through different portions of the release notes. So if you go back to that page that I showed earlier, if you go to the user's manual and then release notes, and you'll see we're going to walk through those. And if you also notice in the release notes for the different descriptions from the new capabilities, there's going to be links to tutorials and guides or extra information that you can find that describe that new capability. All right, this webinar is being recorded. We'll post it to the website too soon. Everybody is going to be on mute to minimize disruptions. Please type your questions if you have them in the chat, and we'll answer them as quickly as we can. All right, now I'm going to turn it over to Tom.
All right, thanks, Matt. I'm going to share my screen and we'll walk through some of the features. So, all right, stop me if you can't see my screen. Hopefully you can. So I'm going to start with some of these gridded precipitation and transposition features. And I'll say that everything I'm about to talk about has been presented previously in one of our quarterly webinars, which happened in the beginning of this year. So you can just browse to, actually, sorry, time flies. It was in October of last year. That's when it was. So you can browse this for the 45-minute version. Today, you're going to get the 5-minute version. So I'll say, use that resource to go in a little more depth. I'm going to start here with the gridded precip. So you see here, we've selected QPE as the gridded precip grid data object that we've selected in the tree. And what you'll notice for precipitation grid sets, now you can specify a storm center X and Y. And all of this is setting up transposition, which just means moving the precip around. So you can set a storm center X and Y. This applies only to precip, at least it should if we did it right. And you can also calculate those based on your data. So if you hit these calculator buttons, it's going to loop through the grid set and find the grid cell of maximum precipitation accumulation and set that as the center X and Y. That's not necessarily always the best place to put it. It's really just a reference point, so I wouldn't get too hung up on it. But you can either use what HMS has given you, or you can specify your own, either way. And this is just used in transposition. So you see there's no red asterisk there or anything. Now, it might make a little more sense if we move on to the MEP model and what it looks like. So this is the MEP model and its component editor. We have a gridded precip MEP model referencing that QPE precip grid. And now you see X chord and Y chord parameterizations here in the MEP model as well. What's the difference between those in the MEP model versus the grid? Well, this is just the origin that we start at, and this is the origin we want to, or sorry, this is the centering that we want to move that origin to. So you could calculate the diff between these X and Ys and these X and Ys, and that's going to be your transposition X and Y. In this case, yeah, the numbers are different. I have not done the math, but there is some transposition going on there. So like I said, take a look at that webinar from October for a little more information. But what this affords us, so we could just specify some parameters and transpose it once, or we can plug this whole concept into the optimization engine and we can optimize that gridded precip. So what you've traditionally done with things like the HMR52 storm is now possible with a gridded storm. So you can either move a historic or optimize a historic storm around, or maybe you have a hypothetical storm or design storm in a gridded format, and you can also optimize that. So that's what this gives us. Matt gave a shout out to some of our sponsors earlier. This one was funded by the USACE General Investigations Program, or the GI program for short. So much appreciated the help there in getting that feature implemented. I think a lot of folks will appreciate that. Moving on to uncertainty and SST, this is getting into the FEMA realm and our FFRD effort. So this actually leveraged a lot of the work we did previously to transpose storms. Now we're going to do this in a stochastic and uncertain way. So what we can do here is we can sample both X coordinate and Y coordinate. And another cool thing is we can actually sample the grid set that we're using. So what this gives us is it gives us the ability to do what's called stochastic storm transposition. And it's another hour-long discussion, but in short, we can start with a grid name and hopefully have a grid catalog, of storms that occurred over a basin, and we can start to sample those storms and sample centerings and get quantify the uncertainty of precipitation over our basin. All right, and then finally, so we can, what was I getting at? Okay, this is just that you can either randomly sample the storms or you can sample them in sequence. Both of those are possible. And then here we can also optimize total storm precip over our basin. So just like we can optimize with our optimization engine with the gridded precip MET model, we can optimize peak flow or stage, things like that. We can also optimize precipitation. That parameter was added to the optimization engine. So that's all I have on the transposition enhancements. I'm going to move on to the next feature that we talked about the webinar. And this is a little lightweight feature, and I think it's a good example of what you all can do. What we can do together. Let's just say that. This just came from the Omaha district, a simple small feature request, and it was to explicitly graft the base flow layers in soil moisture accounting. So soil moisture accounting, previously, we only showed one output time series for base flow, which was the combination of all of the base flow layers. If you know soil moisture accounting, you can have 1 to 3 base flow layers. And we previously just output one, you can visualize one, and the request was, can we visualize each one independently? And it just came from Omaha, and we looked at it and we said, yeah, I don't think that will be too much work. We gave a cost estimate, and within a few weeks or months, this feature was implemented. So what you see here, this dark blue line, that's just the combined base flow. That's what you got previously. This feature enhancement is just, you can see the independent contributions from the different base flow layers, layer 1 and 2. So I think this is a cool feature. I think it'll help a lot for calibration because, as you know, with base flow, it's often a matter of calibrating these parameters to get the correct receding limb of the hydrograph. All right, moving on. Global editor sorting. This is really simple, but worth stating here for your all knowledge. And that's just that the sorting option it was previously labeled hydrologic order, and now it's labeled watershed explorer. There's 2 options there, and that is now watershed explorer and alphabetic. So the thing to know is that the global editor is just going to mirror whatever's in the watershed explorer and the order of the elements there. So if you sort these, if you do a custom sort, because you can change the order here, that is still, as far as HMS is concerned, that is still hydrologic order. So there's not like a user specified order and a hydrologic order and alphabetic. It's kind of like whenever you sort these, you're kind of overriding hydrologic order. So to clear things up, instead of saying hydrologic order here, we just call it watershed explorer. So this is, like I said, it's just going to mirror the order of things over here. All right, moving on. How many people knew we had a basin element inventory table? You don't have to respond, but that was a feature I honestly had forgotten about until we kind of dug this up. This does exist. I think it's parameters menu. I can't tell you off the top of my head, but it's just a basin element inventory. So there's a basin name and an element type. Traditionally, basin name and element type. What we did is we actually rewrote this whole table, and as part of the rewrite, we added drainage area, which is kind of a cool feature. So now you can see all of the elements in your basin model, the type of the element, and then the drainage area to that point. So just a small enhancement to a feature that we've had in the program forever that might have been underutilized. Maybe you'll see a little more utilization now with that feature. We will see. All right. DSS 7 migration. So I don't know how much you all follow DSS and what's going on there, but there's been an effort over the past, I don't know, 5 or 10 years to get this DSS 7 mainstream, DSS version 7 mainstream across all the HEC apps. And so HEC-HMS is jumping into the fray, trying to help get that migration there by supporting DSS 7. We've actually always supported it, but what was happening is whenever we created new files, we were creating them as DSS 6. And then within the past year, we finally got to the point where we could test all of our testing data sets and feel confident in this new DSS7 to the point that now we've set HMS such that when you create a new DSS file, it will be created as DSS version 7. So we can work with both, but now new files are being created as 7. And we also added this migration utility that will migrate all of your files to DSS7, so from 6 to 7. This is on the Tools, Data, DSS, Migrate to DSS7 menu. So the cool thing about this tool is it's extremely flexible. It's going to default to your project directory, which here I have SPK Truckee specified. You can reset that path to anything. You could set it to your C drive and hit OK, and the program would eventually migrate every single DSS file on your C drive. Or you can set it to a specific DSS file. So it's a really flexible tool. I would say best practice at this point is going to be to go ahead and migrate your projects to DSS7, especially if you run into any issue that seems like it might be 7, because the first thing the DSS team asks me whenever I have a DSS issue that a user might have stumbled upon in HMS is they ask me if it's 6 or 7. And if I say it's 6, they say migrate it to 7 and then see if the issue is still there, because they really don't like dealing in 6 because it involves a lot of legacy Fortran code, and the DSS7 is written against a lot of C++ code, which is far more serviceable. So I would say best practice is to migrate to 7. In addition to those serviceability benefits, there's also the benefits of performance. So we've seen in a few cases where 7 is more performant and there is no intent to make 6 any more performant because it is a thing of the past. So all of the current and future investment is in 7. All right, this is kind of a fun one. User interface themes. We've finally got to the point where I had a little time just to implement this, so I did. It was not too difficult because Java UI themes look and feels are it's a pretty flexible arrangement. Let me just see if I can pull this up for you and demonstrate really quickly. I have HMS pulled up in the Windows system theme, which you're probably very familiar with. This is probably about what you've looked at for the past 15 years. What's available now, if you prefer to save your eyes, is a dark mode. There's also a light mode too. So let's just go to Tools, Program Settings, and on this menu now, you see this theme setting. So this is System. System's just going to try and look like the system that you're operating on. So we're operating on Windows right now. It's going to try to look like native Windows. If we're on Mac OS, it'll look a little different based on what native Mac OS UIs look like. Here, we're going to go to dark mode. So I can just change it to dark mode. And there we are. There's dark mode HMS. So that's pretty nice if you're like dark mode stuff. I think it's kind of funny because like command prompts, the original computers were like dark mode. And at some point in the past, we got to like light mode everything. And now we're kind of going back to dark mode, saving the eyes. So there is also like I mentioned, a form of light mode, which is like a more modernized user interface, I would say. And then dark is just the dark version of that. That's that. And then finally, one more from me, and that's this display global editors outside of desktop program setting. Another one that's been in there forever that you may have forgotten about. So let me just remind you of what this is. The reality is it's gone away, so it doesn't really make a difference what it was. It's gone now, but let's just go to Tools. Well, actually, let me do this. So I have my base model selected. If I go to the Parameters menu and say Loss, Initial and Constant, this global editor is inside of the desktop. See that? And I think most users were not utilizing that feature unless they liked it for some reason or on a laptop. So we actually, in the past couple of years, we rewrote all of our global editors, and a simplification to that, we made them say the new global editors are much improved. They have a lot of nice features, but as part of that rewrite, we did away with this. And so what you'll notice in the latest version of the program is that this program setting is gone, and the behavior will be as if this was turned on. So I'll just turn it on real quick and show you what this looks like. So if I go to parameters loss, this is outside of desktop. So I can move this anywhere I want. So some of our reasoning is that we thought most of our users were using global editors in this manner. So we decided that no longer supporting global editors inside of desktop wouldn't be a huge loss. So I apologize if that was your favorite way to do globals. It's just not there anymore. That's all there is to say. All right, I am going to pass it on to, I think Josh is up next.
Yep. All right, thank you, Tom. Go ahead and get my screen shared here. All right, so the first group of features that I'm going to talk to today are all related to sediment and debris flow modeling. So I did just want to reiterate the link that Matt showed earlier. If you go to the training page, and he was actually specifically showing off this post-wildfire debris flow course. And so there's like 3 days worth of material here that I'm going to just gloss over in a couple minutes. So just wanted to let you know of this, just in case you wanted to dive into more detail. All right, so the first thing that I'm going to talk about is a brand new surface method available in version 4.11, and we're calling it dynamic surface. And this was implemented specifically for a phenomenon that we often observe during post-wildfire scenarios. So I've got a little graphic that I'm going to share here from the National Weather Service that hopefully will kind of better explain the intended use case of this new surface method. So on the left here, we have pre-fire conditions. We have a surface layer and a soil storage layer with, we'll say, normal infiltration rates. And then what happens during a fire is that you get this high intense heat that vaporizes a lot of water repellent compounds. And then those vaporized compounds, when they touch the cooler soil layer below, they tend to condense and form this hydrophobic layer that results in really low infiltration rates. And so what this new surface method does is it models the really low infiltration rate that you typically see right after a fire event, and its gradual recovery to hopefully something similar to the pre-fire condition. So a very useful method if you're doing post-wildfire modeling. The next few things I'm going to talk about are all related to sediment results. So first off, we have a new time series type. This is for sediment volume. And this is actually computed from the sediment load time series, which has been in HMS for many, many versions now. But it simply takes that load time series and then multiplies it by user-specified unit weights for each of the soil grain sizes to create this volume time series. So what you're seeing here is total sediment volume, but you can also break it down into volume specifically for each of your soil textures as well. All right, on a similar vein, we have a new bulk flow time series type. And this is kind of a combination time series. It combines the regular flow time series type in HMS, which is water only, with sediment flow. In some scenarios of sediment modeling, the bulk flow time series is going to be very similar to the water only flow time series. But there are scenarios, and one example would be after a wildfire where you have large rates of erosion, where this bulk flow time series can be significantly greater than just the water only flow time series. So definitely some use cases where this new result can come in handy. And then lastly, for sediment results, we've made 2 new column additions to the global summary results table. So if you have a basin model in HMS that is enabled for sediment, and that basin model has been computed, then you will see these 2 new columns. So we have one for sediment load, and then one for sediment volume, with values for each of your elements in your basin model. So this was a kind of a simple enhancement, but it is a time saver, because before, to get to these same results, you'd have to crack open the output DSS file and do some calculations yourself. So really just kind of a convenience thing there. And then the last 2 sediment things that I'm going to talk about, we have a new transport potential option that you can select. We're calling it the sediment delivery ratio. And as its name implies, you have different ratios that you specify for the different soil texture types. If your ratio is greater than 1, that represents an erosional situation. And if it's less than 1, that represents a depositional situation. And then we have a new sediment routing method for reaches. We're calling it the Muskingum method. It uses Muskingum parameters and has these different attenuation coefficients and travel times that you can specify for each of the grain sizes. So this helps you account for the different speeds and the different attenuations that you might see as different grain sizes are routed through a reach. All right, well, I think that's it for the sediment stuff that I wanted to talk about. And the last thing that I'm going to mention here is the newest compute type in HMS. This is only available in version 4.11, and it's the ensemble analysis compute. So if you're not familiar with ensemble modeling, I like to think of it as a model that sits on and leverages other member models. In HMS, you can think of it as just a collection of simulation runs or a collection of forecast alternatives. So I've got another little graphic here that hopefully explains this a little bit better. So we call the base models that make up an ensemble model members. And then in this example, we have 3 different members, which are in HMS. Again, they can be comprised of 3 different simulation runs. Each of those runs are ran individually. You get the individual output. In this case, it's a hydrograph. And the ensemble model will take the individual hydrographs and then aggregate the results into an ensemble result. So in this case here, I have the ensemble creating an ensemble average time series. So it's just looking at the simulation time window for each of these 3 members. And for each time step, it's plucking 3 values, 1 from each member, and then averaging it to create this time series. So there are a lot of different ways that you can apply ensemble analyses in HMS. I think probably 2 of the most important ways, or maybe the most used ways, are going to be to look at uncertainty in your boundary condition data, and then also to look at uncertainty in the basin model methods selections that you use. So in this example that I have over here to the right, I've got 3 simulation runs set up. I'm keeping the MET model the same in each of the simulation runs, so the same precepts being applied. And what I'm changing is the transform method for each of the basin models. And so what this is going to give me an idea of is how my selection for transform can lead to uncertainty in the output. You could also flip this around and you could keep the basin model methods. So same base flow method, same transform, all that good stuff. And then you could just alter the boundary condition data. And so I actually have an example of that set up in HMS that I'll talk to here briefly. So I've got my ensemble analysis created. It is composed of 5 different simulation runs. I'm using the same basin model for each of these simulation runs. The one thing that's changing, though, is the precept applied to each of the MET models. In this case, I'm using a different forecast for each of the simulation runs. So what this is going to tell me is it's going to tell me how the uncertainty of the forecast and the different plausible range of results that I might can expect. So I've already computed this. I'm going to go to the results tab. And we're going to look at an outflow plot at a junction. And since I have 5 ensemble members, I have 5 outputs from each of the members, and those are represented in the colors here. And so I'll just kind of highlight them. And as you can see, 3 or 4 of the forecasts, there's kind of a general consensus, but then we do have this one sort of outlier that's predicting a much more extreme response. And so this is just in a nutshell, this gives me a lot more information than I would have received if I would have just ran one forecast. And as a decision maker, maybe I look at this and I say, you know what, I'm going to be conservative. I want to prepare for kind of the worst worst case scenario. And so I'm going to use the ensemble outflow maximum right here, just to be conservative, and I'm going to make my decisions based on that. Or you could look at it and say, you know what, I'm going to go with the kind of the consensus of the forecast models, and I'm going to use something more similar to the outflow mean to represent that. So just a couple quick examples. I encourage you to look at the tutorial and guides. We have 3 different ones set up that kind of cover other ways that these ensemble analyses can be used in HMS. So that's it for me. I'm going to pass it over to Matt.
All right. Thanks, Josh. All right. I had to experiment with dark mode for a minute after seeing Tom show it. I've heard about that. I just haven't played with it yet, and I had a chance just a few minutes ago. I'm not sure I'm there yet visually to use dark mode, but I'll give it a try. All right, switching gears, let's talk about hypothetical storms and frequency storms. These 2 precipitation methods in HMS have undergone a big change over the last couple of years. And so there's still a few things to kind of work out here. Within the hypothetical storm you'll see on the screen right now, you can now vary the precipitation spatially. So in the past, prior to version 4.11, you could only have 1 total storm depth for all subbasins in your basin model. So that storm depth would be the average of all that area, but you can only apply 1. For areas where precipitation varies across the watershed, so in the mountains or along the coast, you would want to do that, right? So you'd want to set up your hypothetical storm so that precipitation can vary by subbasin. And now you have that option. It's at the bottom of the component editor that you see in that figure right there. And there's 2 options, right? So if you're using NOAA Atlas 14 precipitation frequency grids, then HMS will automatically compute those subbasin depths for you. If you're not using NOAA Atlas 14 grids, if you're specifying the total precipitation depth by hand, then you're going to have to go to each of the subbasins in your basin model within the meteorologic model here and enter those total storm depths. So that's a nice new option. Let's jump to the frequency storm. So this should look familiar right here. This is the component editor. If you're using uniform precipitation for all subbasins, there's that component editor, that table at the bottom where you specify the depths for each of those storm durations there. The feature that was in 4.10 that I just can't stop talking about, you can't really see it right here in this figure. There's a precipitation frequency calculator. That calculator is going to compute the average depths for you, right? So it's the average precipitation depths for all subbasins if you have uniform for all subbasins, or if you have variable by subbasins, and it's going to compute those depths per subbasin for you. So what this figure is showing you is now you can supply the 10-minute, the 30-minute, and the 3-day durations. In the past, HMS versions 4.10 and older would compute the depths for those durations for you based on the precipitation at 5 minutes, 15, 1 hour, and then 2 days and 4 days. So now, since NOAA Atlas 14 provides you that precipitation frequency information, you could enter that information or have HMS compute those depths for you. If you're forward migrating a project, then what's going to happen is HMS will use the same linear interpolation or interpolation equations that were used prior. It'll compute the 10-minute, 30-minute, and 3-day for you, put it in the table, but then you can override it if you want to. All right, and then the last thing for the frequency storm, if you do have that variable by subbasin option selected, and then you either enter all the depths for each subbasin or you have HMS compute the depths for all subbasins, there's really not in the HMS user interface a global table that shows you all of that information in one place except for the precipitation frequency calculator that you see here. So this is the calculator, it's computed the depths per subbasin. And so what's new in version 4.11 is there's this export button. You can click that export button. It's going to create a CSV, a comma delimited file for you. And then you could open those subbasin precipitation depths in a Excel file if you want to. So that would be for your reporting, if you wanted to report precipitation frequency depth by subbasin. All right, let's move on to optimization trials. Greg Karlovitz on the HMS team, he's adopted the optimization tools. He takes feedback from the field. So whenever you all report something's not working as well as it should be, or if you have ideas, Greg is cataloging all of those, he's archiving. We have a system that we use to track all of the feature requests. Greg's tracking all of those for optimization. And when he can carve out a couple of hours here or there, he adds new capability or improves upon capability that exists in the software. So we have for optimization in version 4.11, there's a new relative tolerance for the simplex search. In the past, if you're using the simplex search method and you choose a tolerance, that tolerance has been an absolute value. And why that matters is it's based on the objective function that you use. So if you're using a sum of squared error objective function, which has very large values, then a really small tolerance, that means that the program is going to be iterating for a very long time. Versus if you're using the root mean square error objective function, which has smaller values, then a smaller tolerance might be needed to get to a parameter set that's fairly good. So now you have the option to choose relative, and if you choose relative, then what we've found is between the different objective functions, you'll notice that the search takes about a similar number of iterations or evaluations to get to a reasonable parameter set. All right, let's jump down to an option here. In the past, whenever an optimization trial is finished, the last iteration or the last model evaluation doesn't necessarily create the final parameter set. The final parameter set could have been one iteration before. The program ran that final iteration and it realized, oh, that's not a better parameter set. I can back up and use this one. So you'd have the parameter set. The time series results, though, that have been reported in the HMS user interface have always been the time series from the very last simulation. What Greg added here is now when the final parameter set has been found, the program, HMS, runs one final iteration with that best parameter set. And so now that the time series that you see in the optimization trial results, those are aligned with that final best parameter set. All right. The next thing is really neat. So now, whenever you view results for optimization or objective functions and the parameters that are found during the search or sampled during the search, you now see that information by model evaluation. So an iteration within HMS is how these results used to be reported to you. An iteration could be one model evaluation, or sometimes it could be multiple model evaluations. And with this new capability to see results for each evaluation, now you have a better understanding for the true space of parameters that were sampled during the optimization and the variability in the objective function throughout the entire optimization trial. Okay. The next thing, parameters, scale factors, why these are important. So just imagine you have a configuration where you have observed flow and two subbasins that are upstream of that observed flow. You can imagine if you're trying to determine a set of parameters where you have constant loss rate for subbasin A and constant loss rate for subbasin B. If those are independent, then what you'll notice with the optimization trial is you're going to have a really high constant loss rate for one and a really low constant loss rate for the other subbasin. So we have scale factors in HMS. Scale factors have not been implemented for all model parameters. I believe for version 4.10, they just work for deficit and constant and initial and constant. So what Greg did is he added capability so that now for the Clark method, the Clark transform method for your time of concentration and your storage coefficient, you can use the scale factor on those, and then also for some of the parameters in the simple canopy method. So that's a huge improvement. If anybody here submits a request to the HMS team to build out the scale factor for the linear reservoir base flow parameters, I owe ya. I would love it. All right, finally, differential evolution optimization. There's now a minimum iteration setting here. And the reason why this is important is some folks have been using the differential evolution search for the PMP or HMR52 storm maximization. And we noticed there that that search was giving up pretty early. I thought it had converged just because the storm was not being centered over the watershed. It was centered outside of the watershed. It was moving around. And after a few iterations of just moving the storm outside the watershed, there's no real runoff. It's just base flow. And so the search was stopping. So folks were having to change that tolerance to a really, really, really small number in order to keep it going. But now you can choose the minimum iterations. If I set it to 10, then the program does not evaluate the objective function to see whether the search has converged yet. It waits until it gets to that 10th iteration, and then after that, then it's going to start evaluating the objective function. Okay, let's jump to rule-based reservoir operations. So a little history lesson with HMS and reservoirs. The method that you can choose right here. In the past, the very first option was a storage discharge curve, right? So outside of HMS, you'd have to compute a relationship between reservoir storage and discharge. Then the HMS team added outflow structures. So in that case, you could supply the program an elevation storage relationship, and then you had options for different outlets. You had orifice outlets, culvert outlets, spillways, dam tops, pumps, and other types of ways to get water out of the reservoir. There's no operations there. That's just based on the physical makeup of the reservoir and the computed storage. HMS would compute the outflow in that case. The third option that was added kind of recently is a specified release. So if you have observed flow and you just want HMS to release that observed flow, but you want HMS to compute the inflow or the elevation based on the inflow that's computed, you could do that approach too. So that's the specified release option. And now with version 4.11, there is a very simplified rule-based operations option. When I say simplify, I mean you're operating to one point downstream. So if you want to operate to multiple locations downstream of the reservoir, you have complex operations or multiple reservoirs operating for certain conditions, then you still need to use ResSim. Again, this capability, the role-based operations capability in HMS is fairly simple. What you can do is you can define the number of zones, operational zones, and for each of those zones, you define rules, right? And so for example, let me just scroll down a little bit more. In this zone right here, the zone is defined by an elevation curve. For each day of the year, you define the elevation and the program takes that information. It also takes a storage target, right? So that when I think of a storage target, I think of your operational curve. So you define that storage target, and the storage target is what the program uses to determine, do I need to make releases from the reservoir or do I need to store more water, right? So if the water or the storage in the reservoir is above the guide curve or the storage curve, then releases are made. If the storage in the reservoir is below the guide curve or the storage curve, then water is held back, water is stored. So you can define elevational zones, you can find storage curves, and then you can also define rules for each of those zones. Here's the 10 types of rules that are available to you. You have maximum release rules either at the dam or at downstream points, minimum release rules at the dam and downstream points, specified releases, and then rate of change rules as well. Along with those rules, now you have gates. Gates are added to a gated orifice outlet, and also for a spillway, those gates are operated to meet those downstream or reservoir targets for releases. And then also there's a generalized outlet. And this generalized outlet, I think of it as a virtual gate, right? So you define the minimum elevation discharge relationship, the maximum elevation discharge relationship, and then the minimum time between gate adjustments. And then based on the storage, based on the zones, the program takes that information, your elevation discharge curves there, and computes the release from the reservoir. All right, and then the final new capability that I want to mention here, it doesn't seem like much, but this is really powerful for reviewers, right? So I've gotten a number of requests over the years where somebody is talking about or mentioning that something does not seem right. The program is creating more volume of runoff than precipitation that's applied to it. And after getting the project and digging through it, I and confirm, yeah, the program is computing more volume than precipitation, runoff volume. And so eventually it's found out, yep, there's a precipitation or a flow ratio that was specified. Now, whenever you use the precipitation or flow ratio options, you're going to get a warning. That warning is just an indication to reviewers or modelers that yes, a ratio is being applied. So that's your visual cue that flow volumes might be a little wonky compared to your precipitation volumes. All right, I'll stop there and turn it over to Mike.
Thank you, Matt. All right, I'm going to talk a little bit about meteorologic enhancements, and I'll tell you why those are important in a second, but stick with me. Major thanks to the Northwestern Division, Columbia River Office, the Mississippi River Geomorphology and Potamology Program, and the USACE Arid Regions Work Unit for funding all these meteorologic enhancements. So in the past, people had been requesting that we migrated the gauge interp functionality to HEC-HMS. So specifically, we added precipitation and temperature options where you could take gauges and interpolate those values, or extrapolate those values even, to gridded meteorologic boundary conditions. We actually enhanced that a bit more to allow for some of the additional meteorologic variables within HMS. Now you can do it for every single one. So what I mean by every single one, you can do this for shortwave radiation, longwave radiation. You can always do precip and temperature, that's been there for a while, wind speed, pressure, and humidity. And it can be simple like this, where I have a single gauge for each one of these meteorologic variables that I want to interpolate, or it could be complicated, right? So in this example, I got like 30 or something like that. So gauges scattered all over the place. We'll interpolate between the individual points and then actually create grids for you. Some additional meteorologic enhancements, we like to call these simplified methods. And I'll show you why here in a second. But the first one up is for long wave radiation. We use the Stefan Boltzmann approximation for that. So let me just show you what that actually looks like. This is simplified because we only expect you to specify what type of atmospheric emissivity method and what saturation vapor pressure method you got to use. And in this case, there's one and only one method for atmospheric emissivity and two methods for saturation vapor pressure. Given those two specifications and no additional parameters, we can compute for you long wave radiation wherever you are in the world. This works for both point models, so lumped models is what I'm getting at. So you have a single subbasin or several subbasins, or gridded models, right? So every single grid cell can figure out what amount of long wave radiation is actually impacting that grid right there. We've also done that for shortwave using the reduced solar constant method. We've also done that for precipitation index humidity, and we've also done that for barometric atmospheric pressure. Show you those ones real quick. So similar vein for reduced solar constant shortwave radiation. You just got to specify the way in which you want to alter the amount of incoming solar radiation as it goes through the atmosphere and actually impacts the ground. Barometric pressure functions on elevation. So as long as we know the elevation of the subbasin or the grid cell, you can figure out what the pressure is or estimate what the pressure is. We assume that we're starting with the standard atmospheric pressure at sea level of 101 kilopascals and adjusts upwards based upon your specified lapse rate. And precipitation index humidity functions on the precipitation that's actually falling at that specific time step. If it's greater than the specified threshold, we actually approximate the wet humidity, you specify what the wet humidity is, and we apply that to the grid cell. If it's less than this threshold, then we actually use this value. Right, so these are simple methods. They're really powerful in that you can go from nothing to something really, really, really easily. These are good in the future. You can use these for forecasting, right? So if you wanted to do some climate change modeling, you can do these for retrospectives where you don't actually have a whole lot of relative humidity measurements, right? For something that you're trying to simulate in the 1950s. And you can actually do this for downscaling, temporal downscaling, right? So maybe I am using daily precipitation estimates. I can still compute you down to a 1 minute time step, whether you're exceeding this threshold or not, right? We can do this all over the place. I really, really like those ones. And we also have spatial results. Definitely wanted to note that. So you can see those spatial results as well if you compute the specific methods that are necessary. And those methods being these new enhanced snowmelt methods. I'm going to skip to that first. First, I want to talk about the zonal editors. If you've done forecasting in the past, this editor should look familiar to you. The top is where you specify zonal overrides, and the bottom is where you specify subbasin overrides or individual element overrides. These zonal modifications are now in there for temperature index snowmelt, which is really, really, really nice. So if you want to adjust the PX temperature for the entire zone, you can specify that PX adjustment right here. Same thing that you got before, you can add, subtract, or use a multiplication factor as well. So you can halve, you can double, you can add 1 degree to it, subtract 1 degree, and you can override down below as well. Major thanks to Damon Black for doing that one. It's going to be a much needed one. All right, now for the new snowmelt methods. So version 4.11 brings along 2 new snowmelt methods. First is the radiation-derived temperature index method. This was actually dreamt up by Mike Fulham and published in 2015. We call it the actual hybrid method because we made a couple of slight modifications to it as well to fit within the confines of HEC-HMS. You get additional outputs within this method. So this is meant to be a bridge between temperature index and full-blown energy balance. You get additional outputs. You also have to specify additional boundary conditions, and that's where these methods really come in handy. Not very often that we know exactly what shortwave radiation was 70 years ago, right? But I can estimate it for you relatively quickly using this method in here. We actually did a whole webinar on snowmelt. So if you remember back to March, and there was still snow on the ground, we were still talking about snowmelt quite a bit. So please go back and check those ones out. We have tons of tutorials and guides that talk about how to set up the parameters for the RTI method, how to calibrate those parameters, and also which parameters are sensitive. So go and check that one out. Along with that, we have the full-blown energy budget method that's available within HEC-HMS now. So you have a total of 5 snowmelt methods: banded temperature index, gridded temperature index, RTI, the hybrid method, is gridded by itself, banded energy budget, and gridded energy budget as well. So lots of choices now within the snowmelt modeling. Same thing as before, you get even more outputs with the energy budget method, and you're required to specify even more boundary conditions. Again, these simplified meteorologic methods that I talked about at first are coming really, really nicely when using these methods, filling some of those meteorologic gaps. Same thing, we covered the energy budget snowmelt method in great detail within these webinars. Please go and check those ones out. And check out the tutorials and guides that Avatar put together. They're very, very, very nice. All right, last thing for snowmelt is expanded selection for parameters, snowmelt parameters when doing an uncertainty analysis. In the past, you couldn't select all of these things when doing an uncertainty analysis. Now we open them all up. So if you want to vary your initial melt rate ATI, if your initial cold content ATI, your PX temperature, so on and so forth, you can select them all. And it's the same thing for energy budget, right? Not the exact same parameters, but you can select all of the fixed parameter values as well and allow those to vary within an uncertainty analysis. And also the same thing for the hybrid or the RTI method. All right, moving on. Finally, I'll talk a little bit about 2D diffusion wave enhancements. We have modified the way in which meshes are stored within HMS to allow for one too many meshes. So in the past, you were limited to a single mesh within a basin model. Now you can do 1 to thousands if you would want to go crazy like that, whatever. Let me know if you actually build a model with 1,000 meshes in it. I'd love to see that. This has all been added due to the thanks in partnership with FEMA, so major shout out to them. And we make continual improvements to the software and to the 2D solver as well. So as the RAS team makes enhancements to the 2D solver, we use the exact same 2D solver within HMS, and we benefit from that. We try and return the favor every once in a while where we make enhancements and the RAS team benefits, but those are a little bit fewer and far between. Version 4.12, we have many, many, many new 2D features planned for inclusion within that one. So for further news on that one, keep your eyes peeled, ears to the ground. We'll be showing you a whole lot more coming up in the near future. All right, that's all I got. Take it back over to Matt.
All right, I'll give you a chance. Let me allow attendees to unmute themselves. So if you have any questions for us, we'd love to hear from you. If you want to put it in the chat, that'd be great too. So yeah, you should be able to unmute yourself if you want to. All right, it looks like we got we've answered the questions that were asked so far. Yep.
Like Matt had said to start with, there's a huge list of features within 4.11. This is a pretty mammoth release. We've just kind of scratched the surface and shown you a couple cool features. Definitely go and check out the release notes for a comprehensive listing of all the new features and bug fixes too.
Right.
Very interested to hear about everybody's experience with that.
I would call 4.11 a must-have upgrade. I know sometimes folks are always asking the question of, hey, if the version of HMS I'm using or working with right now is already good for me, why would I ever upgrade? I think if you take a little bit of time and look at those release notes and just pour over not only the features, but especially the bug fixes, there's a lot of not only like quality of life things that are in there, or things that used to be kind of annoying to deal with, or workarounds that we've had to work on in the past. 4.11 is a really, really polished release. So I think this is going to stand the test of time as not only kind of landmark release in terms of all the features that we've got in there, but also kind of elevating the quality and the expectations we have for ourselves on those releases. So big deal release. Highly recommend. You know, here it'll be out soon. The trademarked soon phrase, but we're anticipating a release here sometime this next couple of months. I don't want to put a date on it because that always jinxes it.
Right. Well, in the last few minutes that we have, if there's no other questions, I guess I have one for Mike, Tom, and Josh. What new feature, just one, you can only choose one, what new feature are you excited about already for version 4.12? I'll go with Mike first.
I only have to choose, or I can only choose one?
Yes.
Thanks. I'm really looking forward to the daily disaggregation of gridded inputs. So gridded inputs take us way back to reanalysis products, go the whole way back to nearly the turn of the 20th century. It'd be really, really cool to disaggregate those down to much finer resolution in a realistic way. Improved modeling that goes way back in time.
Yep. All right. Cool. All right, Josh, how about you? What are you looking forward to?
I think I'm looking forward to the importer tool that Daniel's working on for the data, the DEMs, being able to automatically bring those into HMS, make that workflow a lot more convenient, efficient.
All right, I like that one. I'm getting excited about that too. All right, Tom, how about you?
Gridded modeling. So we're doing a lot of work to make gridded modeling easier. If you've done gridded modeling in the past, you probably know its difficulties. So that should get a lot easier in 4.12.
Cool. All right, and I'll go last here. I don't know if it's going to make it in 4.12, so there's no pressure. Greg and the HMS team and the core, there's other people throughout the core, are leading an R&D effort to improve how we do hydrologic modeling for hypothetical events, right? And so one of the things that they're looking into is adding capability to HMS to sample characteristics of the storm. So your time pattern for the storm, your area reduction curve for the storm, the spatial information for the storm. Wrapping all of those options within the uncertainty analysis framework really gets me excited. It's something that it'd be great if we could have done it 10 years ago, but we're finally getting to it thanks to the R&D program. So I'm really getting excited about that. Okay, well, let's close this one out. Final thing that I have is I'll put it in the chat real quick. So that's the link to the page where I'm going to post the webinar. So we'll process it, we'll get it into YouTube, we'll post it to that along with, well, there's no PowerPoint slides for this one. It's all in the release notes. Please check out the release notes. If you have any questions about new capabilities, we would love to hear from you. If you have ideas, we'd love to hear about you too. And please take the time, if you do run across an issue, send us the report, give us your project so that we can reproduce it. Again, we're going to get those fixes out to the field, and you're going to save the field pain and anguish. So we really appreciate it. All right, well, I'll turn you loose. Have a great rest of your day.